Hello. In this video, we are going to derive an expression for the drain current in a MOSFET transistor. So basically, we're deriving the MOSFET model, and we're going to come up with different expressions for that current depending on what region of operation we are in, whether cutoff, triode, or saturation. And so our objective here, we're talking about deriving a mathematical model, is deriving a mathematical expression for the drain current. Which we have referred to as ID. Now, by definition, the mathematical expression for current is defined as rate of flow of charge, dq dt. If we assume a linear model, we're going to approximate that as delta q delta t. And so basically in our model, we need to come up with an expression for delta q, an expression for delta t, and then take the ratio of the two in order to come up with an expression for our current. Now we're going to note that the gate structure, the MOS structure that's connected between the gate and the substrate, resembles that of a parallel plate capacitor, and we're going to use that approximation in our calculations. Sometimes that's referred to as the MOS capacitor. I'm going to draw it as a three-dimensional structure, just so that I can apply some of the, measure some of the geometric distances. But in essence, this is what it is. And so that will be the silicon oxide, and then at the top and at the bottom, we will have two pieces of conductive material. At the top, we have the polysilicon or metal, and at the bottom, we will have the body or substrate, where we have induced, assuming we have applied the right voltage, at the gate, we have induced an inversion layer, and so it becomes conductive as well. So I'm going to represent those with a darker color. Basically, that's our MOS capacitor. It kind of looks like a sandwich. I'm going to write down the expression for my capacitance. The generic expression for the capacitance of a parallel plate capacitor. So the capacitance is proportional to the area of the capacitor. And the area is going to be the width times the length, assuming a rectangular shape. It's inversely proportional to the distance, and it's going to be, the proportionality constant is going to be the permissivity of the insulating material, in this case the permissivity of the oxide. Now I've labeled the distance. The distance will be the distance between the plates. We typically are going to refer to that as the thickness of the oxide. And so I can rewrite that expression as being the permittivity of the oxide material. Typically the permittivities for different materials are tabulated. Width times length, that's the area, divided by the thickness of the oxide. And now we have come up with an expression for the capacitance that relates to the MOSFET parameters. I'm going to refer to that as the gate capacitance, or CG. Now, based on this model, I'm going to go ahead and find an expression for delta Q. Meaning the delta of charge. And that's assuming I apply some kind of voltage. So let's imagine I have biased my transistor by applying a corresponding VGS. Otherwise, my charge obviously will be zero. I will have no channel induced or anything. And then I'm going to apply a voltage differential between source and drain. Maybe I'll just represent it with another voltage source here. That's VDS. All right, so my delta Q, it's going to be related to the voltage that I have applied meaning my rate of charges or my difference of charge is going to be related to the voltage that I have applied, and the relationship is determined by the capacitor equation, which basically tells us that the delta Q is related to the delta V, and the proportionality constant is the capacitance of the capacitor. I'm going to say delta Q equals C sub G delta V. All right, so in this case I have delta Q, again, equals Cg delta V, and my delta V is going to be the delta between the voltage at the gate and the voltage underneath the silicon oxide, the voltage in the channel. Okay, that is the electric field that is being applied across the capacitor. Now the voltage is going to be different depending on which point I measure. Not at the gate, but underneath, if I measure it really close to the source, the voltage is going to be 0, because the source is directly tied to 0. If I measure it right at the drain end, the voltage in the channel is going to be equal to VDS, because that's the voltage that I am applying at the drain. And the voltage is going to decrease from VDS to 0, and so the closer I take my point, the closer to the source, the closer to 0 I will be, the closer to the drain, the closer to VDS I will be. It makes sense to go ahead and just take the average of those voltages, meaning, whatever the voltage will be at the midpoint underneath that gate. And so that's what we're going to do. And so when I talk about delta V, it's going to be VGS minus the voltage at that midpoint, which, if we are assuming a linear progression of voltage, it will be 1/2 of VDS minus VS, basically 1/2 of the VDS voltage. So this will be Cg. And it's important to note that the voltage applied at the gate, we're not going to consider just VGS, but rather VGS minus VT. So the overdrive voltage, that's the effective voltage, if you want to think of it that way. And so VGS minus VT, that's the gate voltage, minus 1/2 of VDS. That's my delta Q, the separation of charge between the two plates. And so I can substitute the value of Cg that I have calculated earlier. It's going to be the E oxide, the permittivity of the oxide material, times the area, which is the product of width and length, divided by the thickness of the oxide. All that times the voltage, VGS minus VT, minus 1/2 of VDS. So I have my expression for delta Q. I'm going to find an expression for delta T. And delta T is going to be related to the drift velocity. As you know, when we have movement of charge, we measure the velocity as drift velocity, and it is related to the electric field. So for a higher electric field, I will have higher drift velocity. It's also related to the mobility of my charges. In this case, since I have n-type material, it will be the mobility of the electrons or of the n-type carriers. And then velocity is related to time, because velocity is equal to dx dt, or distance divided by time. So I can say since v equals dx dt, which I can approximate if I'm applying a linear approximation as dx dt, delta x delta t, excuse me, then I can say that delta t is approximately equal to delta x divided by the velocity. Delta x, in this case, is going to be the length of the channel, because the electrons are moving from one end of the channel to the other. So that's the length that they traverse. And v will be the velocity of those mobile charges, which again is related to the electric field and the mobility of the particular type of charge. So I will have delta t being equal to the length divided by the drift velocity, which is mobility of the n-type carriers times the electric field. Now, the electric field that is causing the electrons or the charge carrier to move through the channel is related to the difference in voltage applied on both ends of the channel, so that VDS voltage. Specifically, the relationship between the electric field and the voltage applied is given by the length of that channel. And so we have that this can be written as L divided by mu sub n times VDS divided by the length of the channel. Or I can rewrite that as L squared divided by mu n VDS. Notice VDS represents the VDS voltage, so it's got nothing to do with the velocity. The velocity is the drift velocity. I'm going to just make a note here. So V equals drift velocity. So it's not confused with any voltage. So now that I have my expressions for delta Q and delta T, I can find an approximate expression for ID. So this will be step number 1. That was step number 2. I'm going for step number 3 now. Find expression for ID. And we're simply going to take the ratio of delta Q to delta T. And based on those two expressions we have gotten, if we rearrange terms a little bit, we end up with the following: mu sub n times epsilon oxide divided by the thickness of the oxide, width divided by length, VGS minus VT minus 1/2 of VDS, all that times VDS. So it's a rather lengthy expression, and so we typically like to simplify things or combine things whenever we can as much as possible. And so the first combination that we're going to do is we're going to note that epsilon oxide divided by the thickness of the oxide, if we look at the equation for the capacitance, it was epsilon oxide divided by thickness of oxide times the area. And so that represents the ratio, the capacitance per unit area at the gate. So I'm going to call that C oxide, the oxide capacitance per unit area. It's the ratio of epsilon oxide to T oxide. And again, that's the oxide capacitance per unit area. And obviously, that times the area will give me the oxide capacitance. We can also see that epsilon oxide and T oxide are going to be constants for a given transistor. So are going to be mu sub n, and for a given transistor as well, width over length. But width over length, we like to consider it separate. That's called the aspect ratio, because when we're dealing with MOSFETs, we're going to see that we often play, and I'm talking more about integrated circuits now, because in a discrete transistor, you obviously get the dimensions that you get and you can change it. But when you're designing with integrated circuits, we'll see that this geometry of the device is something that we can play with, that aspect ratio. And so we're going to combine the mu sub n with the C oxide, and so we're going to let mu n C oxide, we're going to refer to that as Kn prime. And because it has units of current over voltage, transconductance unit, we refer to it as the process transconductance parameter. We refer to width over length as the aspect ratio of the device. And we typically label the transconductance parameter times the aspect ratio as the MOSFET transconductance parameter or the transistor transconductance parameter. Because again, if you look at the overall expression, mu n epsilon oxide over thickness oxide times the aspect ratio, that gives you the transconductance. It will be basically the output current divided by the voltage. And so it has units of current over voltage again. And so that's typically called either the transistor transconductance parameter, or I guess I haven't defined it yet. Maybe I'm getting ahead of myself. So this is going to be Kn prime times the aspect ratio. That will be the MOSFET transconductance parameter. Or the transistor transconductance parameter. Alright, and so we have our final equation, ID, which can be expressed as K sub n times VGS minus VT minus 1/2 of VDS times VDS. If we wanted to still simplify that expression a little bit more, we could just keep in mind the fact that VGS minus VT refers to the overdrive voltage, and so I could really rewrite this as Kn times the overdrive voltage minus 1/2 of the drain to source voltage times VDS. And that's my expression for current. First thing to notice is that there is a quadratic relationship between ID and VDS. We have VDS inside the parenthesis there, and then it's multiplied times another VDS. And that's something that we're going to see in the MOSFET transistor. There is that quadratic relationship between ID and VDS, which is different from the BJT transistor. Let's go ahead and look at the expression and how we can simplify it for the different regions of operation. In this case, we have assumed that we were out of cutoff. We have assumed that VGS was greater than the threshold voltage, but we do know that as a first approximation, we have the cutoff region that we are in whenever our VGS is less than the threshold voltage. And obviously the expression for current in that region is just 0. Then we have our triode region, and the conditions for triode, where first VGS must be greater than the threshold voltage, and VDS is less than the overdrive voltage, VGS minus VT. And in that case, we have our expression for current that we just have come up with. ID is equal to Kn times VOV minus 1/2 of VDS times VDS. And so we have that ID is basically a function of VDS. And we can approximate that behavior, we can model it as a resistor. And so if I wanted to think about my transistor from source to drain, I will basically have a voltage dependent resistor where the value of that resistance depends on VGS and a little bit of VDS, because we can see that the curve is not perfectly linear, but it's especially towards the end as we approach the saturation region, there's a little bit of an asymptote there. And then finally we have saturation region, where the conditions are again that VGS be greater than VT, and we enter saturation whenever VDS is greater than or equal to VGS minus VT, the overdrive voltage. In that case, we can replace VDS by the value VGS minus VT in our equation up there. And so we will come up with the following. We will have ID equals Kn times, and then we have the overdrive voltage minus 1/2 of VGS minus VT, and all that multiplied times VGS minus VT. And so when you put all of that together, you come up with 1/2 of Kn VGS minus VT squared. Where, again, what I have done is taken the value of VDS equal to VGS minus VT, the value when I enter the saturation region, and replaced VDS by that value in that equation, the generic equation. And so, as I mentioned before, we can see now that once we enter saturation, there is that quadratic relationship between VGS and VGT. I can also write this as follows. ID is 1/2 of Kn times the overdrive voltage squared. So either one of those will be valid. We can see that ID is independent of VDS, excuse me. It's only dependent on the overdrive voltage square, and so therefore I can model this as a current source. Current flowing from drain to source. That's ID. And the value of that current is related to VOV squared. And again, notice that quadratic relationship between the current and the input voltage for a MOSFET transistor, as opposed to the exponential relationship that we had in the case of the BJT between the output current and the input voltage, given by the Shockley equation. So that will be cutoff. ID equals 0. Triode and the conditions, that will be the value of ID. Saturation, those are the conditions. This is the expression for the current. And those will be our models. I forgot to mention, for the cutoff case, we can simply model the transistor as an open circuit where there is no current flow. We can go further ahead and draw our curves. Our IV curve of ID versus VDS. And we can observe the following. Well, we already had mentioned that for cutoff, the current will be 0. But for any other case where the gate voltage VGS is greater than the threshold voltage, or for a non-zero overdrive voltage, we will have the following curve. And so basically we will observe that for small values of VDS, we have almost a straight line, so a quasi-linear relationship. So for small VDS, much smaller than the overdrive voltage, we have almost a straight line. So basically a resistive dependency between VDS and ID. And the slope of that line is 1 over the resistance, which we refer to as GDS, transconductance, which is 1 over RDS, which is the drain to source resistance. And if we go to the equation for the triode region, we can see that this is approximately equal to Kn times the overdrive voltage. That will be the value of the transconductance in that region. You can see that as VDS increases, the slope of that line decreases. So that's something to note. As VDS increases and gets closer to the overdrive voltage, the slope decreases, which means that RDS increases. And then basically at some point, which is when VDS is equal to the overdrive voltage, then I enter my saturation region. And my current will remain relatively constant afterwards for further increases in VDS. And this is the point where I have current saturation, where the current becomes almost constant due to the channel pinch-off that we have talked about. basically IDS approximately independent of VDS. And that's it. We had, again mentioned, we have the three regions. I guess we can represent the cutoff with a different color, just for distinction. We have the region of cutoff, triode, and saturation. And now we have a mathematical equation to come up with expressions for the drain current ID for all three of those regions. Thank you.